Okay, well, we're recording. So this is training session on the ReEDS model. We'll primarily be focusing on the 2020 model version, which is the model version that is publicly available today. So the version that you could go out and download now. And we'll start it off with Max. I'll let you go ahead and take it away here.
Can you see this?
Yep.
Awesome. So, hi everyone. My name is Maxwell Brown. Thank you, Wesley, for introducing. So, what I'm going to start with today is just how do you approach running ReEDS from the beginning. So, if you don't know anything about ReEDS, if you don't know anything about what we're doing here, trying to give you a very brief background of what the model is, what it does, how it functions, how to think about the model structure and interacting with the model. If you don't know ReEDS at all, what ReEDS is the capacity expansion model. So what it does is it minimizes the costs of of operations and investment across a specific time period, a user-specified time period. Typically, we solve this 1 year at a time. So we'll say we'll solve 2010, solve 2012, do our operations in between as needed. But you can really think of this as what is the minimum cost needed to meet our major constraints, which I've listed here. One of the key characteristics of ReEDS, it is the regional energy deployment system. And something to think about here is that it has this relatively high spatial resolution relative to other models. So we have 205 balancing areas. In this case, in the public version, we have 134 US balancing areas. And this is really where, supply must equal demand. So electricity generation plus net trade must equal load. And then we also have these subregions, and I'll show you a map on the next slide. But really, this is just we have the balancing areas, which is where supply must equal demand, and then you have the. Sorry, I'm going to move this real quick. So what we have are the balancing areas and the supply regions. And if I look at a map here, this guy. So here, all these different P's that we're looking at. So if we look at North Dakota, we have P37 and P36. At those locations, we really need, the model will require that the amount of generation plus net transmission must equal the load required. And then you have the other operating reserve constraints, you have planning reserve margin constraints, all those sorts of things. And then at these subregions are where you can build certain types of renewable energy capacity. So you can see P37 has that's where we have to meet load, but I can also build capacity at these subregions. One thing we did, this started in 2017, was we scrapped all of the existing code base and we started rewriting everything from scratch. And in doing so, we added a bunch of different things that kind of help us make the model flexible, put in a bunch of features that we wanted for a long time. So to spell those out, we have user-specified years, meaning before we were always solving 2010, 2012, 2014. But now you can say, oh, I want to solve 2010, 2020, 2030, 2040, 2050, or 2031, 2032, 2033. All those sorts of things are just gives us the ability to very, shrink down the model, bring the model back up, those sorts of things. And I'll talk about this technology resolution. What we've done before, this is usually where people get tripped up. And I'll just be honest with that. We have this V index in the model. If you've used the model before, you've probably seen it. And so I'm going to go through exactly what that V index means. We have explicit tracking model plant vintages, meaning I can go down to the unit level resolution or aggregate up to have one representative unit for all existing technologies. We have different types of time horizons, meaning we can solve a myopic view. I'll solve 1 year at a time, not knowing anything about the future. Maybe I want to see 5 years into the future, which is the sliding window approach, or I can solve having full knowledge of everything in front of me, which really just means, if I'm sitting in 2010 or 2020, 2021, 2022, I know exactly what's going to occur in 2050, and I'll adjust my decisions accordingly. We do allow for endogenous retirements and refurbishments. I'm not going to go into a lot of those. There are switches in the cases.csv file that explain how to activate or deactivate those assumptions. Significantly shorten the code length. And one thing we've revived, at least in the 2021 version, is we do have this iteration with the detailed residential demand side. So that's functioning again. I used to have this asterisk on here that just said, if you use this, beware. But now I'm pretty certain that if you do want to boot this up, it works with either myopic or the full intertemporal mode. So, and again, if you're very new here, here's our web page. go online. You'll need to register to get access to the model, but after that, it's a pretty short and quick step to just get to the GitHub repo, clone things, all those fun things. So we're going to get started really quickly here. So what I do, if I go into the model, well, the first thing I'm going to do is we have to know what cases you want to run. Now, it's very easy to run the reference case. If I'm looking at my repo here, so I'm going to get rid of this guy, clear things. If I'm looking at the very base of my repo, I have these different files here, but the one thing that I'm going to look at are these different cases. So in the very beginning, if I just go to this cases.csv file and open this up, take a second. What I know is that there are these different settings here. So I'll change this to ref. But what I can do here is there are all these switch settings. So in this very first column, in column A, we have the different switch. So we can say, for example, what is our UPV scenario going to look like? I'll zoom in for those of us that can't see well. But for example, here I have my UPV scenario. And by default, I can have my UP. So in the second column, we have the description here. And the default is going to be this UPV ATB 2021 moderate. But I could just as easily say, UPV ATB 2020 moderate, and allow myself to just switch the costs for these UPV technologies, UPV being utility scale photovoltaics. But there are all sorts of different switches in here. So these first ones up at the beginning define kind of, so for example, here is my natural gas price scenario. And I can say, oh, ATB AEO 2021 reference case. Or in this case, if I want to change something for this case, this column here, so if I want to switch this to high oil and gas resources, I can add this switch here to tell the runbatch.py script, which we'll go through in 1 second, to make that change for this case. So for this case, what I'll call HOG in this situation is it's going to get that name when I run this scenario. So what runbatch.py will do is it will grab each one of these, unless I specify ignore, so you can choose to ignore. That becomes useful when you start really running lots of different scenarios and going back, checking results, rerunning things. But what will really happen here is I'm going to call this case HOG, or HOG, high oil gas resources. And when I run this case, I'll show you this in a second, it's going to create a directory in the base of the repo. First, it'll create a directory called runs, and that's going to store all of my information for my different runs, so for my different cases. And then it's going to create a directory with the user specified prefix there that says run / in this case, I'm using demo underscore HOG, or I could call this high oil gas resource. Anything I want to do up top, make sure you don't put it, usually not periods or slashes or those sorts of things that are going to throw errors, but we typically stick to these underscores here. And if I wanted to, I can show you real quick. So I created, in this case, I created this demos.csv. So I created a cases.csv file, and here I have two different switch settings, two different cases that I want to run at the same time. Now I have my reference case, which will default to all of these default options that are in column C, and I have my high oil gas case that is right here. So I have my AEO 2021 HOG case. Now, what happens is I'll do a call. So here, when I'm at the command line in my repo, here I'm using the terminal, I can say python runbatch.py, and I can say, what do I want to prefix these cases with? So all of the case names that we've stored in cases.csv, those are going to be used as to identify what cases are going to be run and how I'm going to interact with those cases. But I can say, oh, well, I want to call these, Max Brown underscore reference, or, Wesley Cole underscore reference, anything like that. And I could say here, if I want to call these Max Brown. Now, when I have my cases.csv file, I named this one cases underscore demo.csv. And so here I can put in the suffix for that case file. I would highly recommend reading through these notes, especially if you're not a Windows user. There's a lot of caveats there that you should be aware of. But here I'm going to say case suffix demo, and it's going to print out. So here are the cases being run. these are our reference and high oil gas cases. So we see these cases here match up with what we see as what's going to be run, and then it's going to ask me how many simultaneous runs do I want to launch. And in this case, so what runBatch.py will do is you can tell it. You can think of it like lines at the DMV, where how many lines do you want, and each case is going to get into line, and it's going to wait. And what will happen is it's going to run all of its scenarios, and the next case that's behind it will hop in line and go through its processes. So for us, I could say one case, run one case at a time, run two cases at a time, do 10 cases at a time. If we're running these big cluster machines, you can do 100 cases at a time if you really want to. What you need to be aware of when you're thinking about how many cases you want to run, one is RAM usage. So depending on all your different settings, you may have a high amount of RAM or a low amount of RAM. I would probably recommend, and Wesley or Stuart, correct me if I'm wrong, probably about 8 to 10 gigabytes of RAM per case, just when you start to get to some of these larger switch settings. So if you're running unit level, if you're running all these sorts of different things, but you can go down to 4, you could go down to less than a gigabyte if you're just running ERCOT. And the other thing to be aware of, and I'll show you this in a second, is there is a number of threads that are going to operate for each case. And so each of these threads, you'll have to know the number of either CPU cores and number of threads per core for your CPU on the machine that you're running. But in general, you just don't want to be maxing out your CPU. It just makes things run a lot slower. It really lags down the system. So be aware of two things when you're running this. One is how much memory you have on your machine. Two is how much CPU power you have available to you. And I'll show you how to change the number of threads per case in just a second here. But what you really need to know here before I say, oh, I want to run 100 cases at a time, can my computer handle that? Well, in this case, I'm pretty certain my laptop could run 2 cases at a time. So I'm going to say run both of these scenarios simultaneously. And when one finishes, let's say I had 4 cases that I wanted to run here, those are going to get in line. And when one of these finishes, this runBatch.py script will kick those off again. I'm going to wait. It does the financial calculations first. And remember that I named these Max Brown, but I'm going to go through another set of cases that I prepared for this demonstration here. I'm going to go through these guys. I'll start up a new one. And what this does really, so I'm going to switch over to these runs that I ran before. So instead of calling these by prefix as Max Brown, I called these Demo 1. And I'm going to have this reference case here. And what this really does is it's going to copy over the files in this files for batch.csv file. It's going to copy those over, and it's going to start issuing some commands. Now, those commands are contained in this call file. So we'll go through this all in 1 second, but really, runBatch.py processes those arguments that we had in that cases.csv. Remember, I had my cases underscore x equaling demo here. Those indicate the scenarios to be run with the different switch settings. runBatch.py processes those arguments providing cases.csv. Now we need to balance this cplex.opt, and I'll show you this in a second once this finishes. But then for each case in this cases.csv, it's going to copy over those necessary files. It's going to copy over the files. Those files are in files for batch.csv. Let's see if this finishes. I don't need it to finish. Oops. Computer's going to start running slow, of course. So I'm going to open files for batch.csv. And what this is, second, this just tells runBatch.py what files are necessary for me to run my cases. So here we want to copy over this Canada imports can't exports.csv. We want to copy over all of our GAMS files from the base of the directory. So you have csupply model, csupply objective, all these sorts of things. runBatch.py, for each case that's in there, it's going to copy over every single file that's listed here. And if it doesn't have a directory specified in the beginning, so these are, we can call this, I'll zoom in, sorry, Claire. So when I run runBatch.py, it's going to copy over every single one of these files. And if it doesn't have a directory prefix here, these are going to get copied over to the root of that run/mycase folder. So for example, here, if I'm looking at Just add a new one, why not? DB runs demo one reference. So what this did, I ran runbatch.py. Everything that's in files for batch is now in my directory. So it copied over all the necessary files that I need to run this case. Now, the other thing that runbatch.py does is it'll create this call file. Now I'm here in my call file. This is the same call file. So we saw, in the same case that we had Max Brown _ reference, we now have demo1 _ reference. And all this does is it issues the command, it creates runbatch.py will create the commands that are needed to run reads and store it in it's either going to be, if you're on Windows, it's going to be a .bat file, a batch file. And if you're on Linux or Mac or anything like that, you're going to get a .sh file. The commands are going to look very, very similar. There might be differences in the directory slashes, directory separations. But really what we have are, if I look at this, all this is doing, it's going to call create model.gams first. And all create model.gams is, I can show you, is really just those arguments that are in cases.csv or cases _ demo.csv or cases _ wesleycole.csv, anything we want. But all of those switch settings that we just saw are passed into create model.gams. So this contains our, we were looking at a natural gas scenario. This gives us the ability to say, I just need that information passed from that beginning runbatch.py script into this model run. And in order to do that, I use these global arguments that GAMS can take from the user and load into its running of code. So here, we could say, we knew that this AEO 2021 reference case, that was our default switch. We didn't change that for this case. And so this allows us to specify the different switches between those. So that's all done in this create model.gams call. So in the very beginning, we say GAMS, create this model using these switch settings. And then after that, most of these arguments that are passed are just different case names, different year settings, different case settings, all those sorts of things. But in the big create model.gams call up front, we're able to pass in the natural gas scenarios, the technology cost assumptions, the carbon policy assumptions, the coal price scenarios, all those sorts of things get loaded in the very beginning. And then after that, we don't really have to worry about them because they're stored in these, I call them GU files, but they're G00 files. So what I'm doing here, I can go through this a little bit. I call GAMS and I say, GAMS, run this model.gams file, which is really just, it's really just appending several different files that we separate just to kind of keep things a little bit more organized. But we have awrite data, which is going to call different Python scripts using those arguments that we passed in from the cases.csv file and create inputs that are needed to run the case. So at awrite data, so to repeat that, awrite data that calls Python for multiple different input scripts using those arguments we passed in from cases.csv and prepares case-specific CSV files that are loaded in throughout the code, but primarily in binputs.gams. So in binputs.gams, we might do something like, oh, I need to load in my fuel prices. In awrite data, I created custom fuel prices for this case in order to change the switch settings to low natural gas prices, high natural gas prices, those sorts of things. C-supply model, in this case, will take the bulk of our, it creates all of the constraints necessary that are necessary for ReEDS to, defines the environment for ReEDS. We need load to be met by generation plus net transmission. We need operating reserves to, be a function of the wind and solar penetration as well as load. We need our capacity credits to be met. All those sorts of things are contained in the C-supply model. And then we separate out C-supply objective. I'll go through just the logic behind that in 1 second here. But then at the end of this, we have dsolve prep, which really just does some rounding, make sure everything's in place for us to call whatever solve file we're going to use. So
hey Max, could you
yes.
hit Control+ to make the font bigger? We just got a question for somebody who wanted to see. Oh, sorry for interrupting. You're on a roll.
Is this good?
Looks good to me.
This
Claire,
good?
I don't know. Feel free to follow up.
Okay.
Anyways, thanks. Doing great.
Sorry, Claire. Thanks, Matt. Appreciate it. So what we're going to do in the very beginning, if you've never used GAMS before, we're going to call this createModel.gams file, which is, if you remember, this is just stacked versions of these different files that we can go through quickly right after this. But what this is going to do, you're going to say, GAMS, create model. We're going to create the the data and the constraints, everything needed to define how ReEDS should operate in this first step. What we'll do then is we're going to save this as GU files. I call them GU files, G00 files, what have you. But we're going to save this. So if I say XS, what that means, you can either say S equals, but we use XS as a compressed save because these files get rather large. But all I'm going to do is what GAMS will do, not me. GAMS is going to call this file, and at the very end of that, it's going to save this G00 or GU file. And you can think of that as just this, if I want to run all of the code up to a certain point and stop there, if I restart from that, I can just essentially append code to where I was just at. So I can save this file and then restart from that file, and all that's going to do is store all the information available to you in a file. And then I can restart off of that using another command. So here we're saving this as GU files /demo_reference. And I'm going to restart. So in my next command, I'm going to call GAMS solve a year, restart from that GU file I just created. We're going to compress some things and then save that next file. So we're solving 2010, restarting from this file that was created through the createModel.gams script through that call. And then we're going to save that as this demo1_reference 2010. So in the next call, we can say GAMS desolve 1 year, GAMS desolve 1 year. We can use that same file then to just keep issuing commands for GAMS to solve ReEDS. In this case, we say, oh, now we're going to restart. So we just saved this 2010 file after solving 2010. We're going to restart from that 2010 file and save this as the 2012 file. And we do that all the way through this. So we go all the way through, even at the end, we'll say, okay, we're solving, we just solved 2040. We're going to save that as 2045. That's how this entire thing will operate, is through this GU file or G00 file restarts and saving. So we're going to save a file, restart from that file, and solve a year. Save that year, restart for the next year. So what happens at the very end of this, one thing to be aware of, so I've already ran this createModel.gams file, and at the end of it, what we're going to get is this inputs.gdx file. And I'm mentioning this right now just because it's extremely useful as you're starting to debug things. Everything that the model is going to see after you've done all your inputs processing, after you've created all your constraints, everything that the model has in it is saved in this inputs.gdx file, especially as it relates to data. So I can open this. And what happens is, so this is the GAMS Studio IDE, and I can look at things like, oh, I want to look at what is the fuel price for this case. I have my coal CCS fuel price for these different technologies. I'll run through these in just 1 second. But I can look at, oh, here's my gas fuel price. Here are my coal fuel prices. All those sorts of things are stored in this inputs case/inputs.gdx file. Very important, very useful. One other thing that's extremely useful is, so I ran before, like 5 minutes before this meeting started, to be fully honest with you, I ran the demo1 reference createModel.gams file, and I ran the demo1_HOG createModel.gams calls. So what I can do here, one very useful tool that not a lot of people use, but gets even more useful as you start to create new inputs, those sorts of things, is Gdx Diff. So Gdx stands for GAMS Data Exchange. It's really the proprietary data format that GAMS uses, but it's really a very quick, I think it's got SQL under the hood, but I'd have to check with GAMS on that. But it's an extremely quick way to navigate through the inputs that are in any sort of, that are in your model. So in this case, what I like to do, and this is just, to help people that are just getting started with this, I can do a Gdx Diff, and that's an internal GAMS command that says, okay, compare, you have Gdx file 1, Gdx file 2, tell me all the differences between these two. So I ran demo_reference, and we had inputs case, inputs.gdx, and we had demo1_HOG inputs case /inputs.gdx. And I can do a Gdx diff on these. And what it's going to tell me is everything that's different between the inputs of these two cases. So all I changed here was in the HOG case, I changed that natural gas scenario and the output from this. So it's going to compare every single thing here. So we'll see, oh, well, there's a lot of things that are different. All of these are related to fuel price. So I can kind of expect that. But if I open this diff file, I see here's everything that's different. One thing to be aware of is you'll have files compared. So file 1 is my demo1 underscore reference inputs.gdx, and my file 2 is demo1 HOG inputs case inputs.gdx. So same command that I just issued, but I can look at things. Okay, fuel prices. If I really want to see what is the difference between fuel prices for my reference case, remember file 1, or my low oil gas price or my high oil gas resource case. So we see in my reference case, my prices are higher than in my low oil gas price case. This just really allows me to do these very quick differences, compare inputs across cases. As you start to work with the model, get it up and running, all those sorts of things, it becomes extremely useful. One thing I also like to do is you can execute unload from a solved run and do the same thing. So I could Gdx Diff after unloading all of the data from my runs, and then I would say, oh, well, you solved to 2050. How does everything change up into that point? So what I just covered was run batch.py, cases.csv, this general create model.gams structure. And what I want to do is go over a few things that usually trip people up. So I've trained a lot of people to run the ReEDS model. And just as a quick recap here, so we have cases.csv defines the options for your case, run batch.py processes those, creates all of the creates the directories and copies over the files necessary to run those. And then we need to balance the cplex.opt. I forgot to show you that, but I can real quick. So in the root of the repo, the default cplex options case, if you have a license for cplex, you'll have this threads argument, and that defines the number of virtual processors that are going to be used per case. And so typically you'll have 2 CPUs, 12 different logical processors, those, and then you have 5 virtual processors per core. I'm just making up numbers here. But what this will do is, if you look at, on a Windows machine, it's a little easier, but you can just see how many threads do I have available to myself. And if I'm running 2 cases and I have 4 different threads per case, I'll have 8 threads being used in total. You just want to make sure you don't exceed that. So that was in cplex.opt. So for each case, copy over those files. We're going to copy over those inputs from wherever in the original repo they're stored from that files for batch file. We're going to create that batch or shell file depending on your operating script, and that's going to contain the options you want to run for that case. And then you have the issues, the command to call that into that threaded queue. Remember the DMV lines where you get in line, you'll run your case, the next person will pile in once you're done. And then call _case.bat-issues commands to run the case. First command is to create model.gams. It goes through these different files. It really just appends those files together. And at the end, you're going to produce these GU files and these inputs inputs.gdx. And then the next steps really depend on the case's temporal settings. But if we're running the myopic case, all we're doing, call create model.gams, again, the very first thing you're always going to do. With the 2021 version, we're going to just solve 2010 to 2020, avoiding Augur. Now, Augur does the capacity credit, curtailment, and storage arbitrage values, and I would highly recommend attending Will's session on Thursday that goes through how to interact with Augur, how to think about Augur, those sorts of things. We have Augur solve, which really just prepares those inputs. So if you're after 2020, so we're going to solve 2010 to 2020, we'll export that 2020 solution to Augur using D3 Augur data dump. Augur solve, it really just prepares inputs, runs the annual dispatch, so it solves for all 8760 hours in a daily chunk at a time, daily 24-hour chunks at a time. It's going to use that solution, compute existing curtailment, compute marginal curtailment, compute storage contributions to capacity credit and curtailment reductions, capacity credits, and then a storage arbitrage value. And it's going to compute the capacity credit for all other technologies. Now, after I've done that, so I'm going to solve 2020, I'm going to run Augur, and I'm going to load whatever Augur tells me are these different capacity credit curtailment scripts into my 2022 solve. So I'm going to take those marginal amounts of capacity credit, the marginal amounts of curtailment, those sorts of things. And I'll push that into my 2022 solve for the GAMS desolve 1 year. It's going to solve for 2022. We're going to export that 2022 solution to Augur, do this same thing, solve 2024, do the same thing all the way through to 2050. And then after that, we'll run these reporting scripts. One thing that is an extreme, when people start to run ReEDS and they want to make modifications to it, one thing they typically want to do is, oh, I want to add this new feature. I want to add, Jonathan Hogland Hand added in the carbon transport and storage representation. What he had to do was he had to add in those carbon and transport costs to the objective function. In order to do that, he added those into both the objective, into the investment and operations component of the objective function. You need to separate out, so the ReEDS objective function will solve a single year, if you're running the myopid case, I'm just focusing on the myopid for now. If you're solving just a single year, it's going to take the overnight cost of capital and weight those in the investment as an investment amount, but it's going to give you the upfront cost of those capital as it would be if you finance those over a certain period of time. And then it's going to weight the operations as 20 years of operation. So I'm standing in 2020, I see, oh, I can invest in this new shiny PV plant, and I need to see how much that is going to cost me over 20 years of time. So I'm sitting here and I weight both my investment up to date with 20 years of operation over time. You can think about that two ways. You could either annualize those payments and say, oh, well, I'm only making a $20 per month payment on that, so I'm going to purchase it, or and I'm only operating it for this year. Or you can say, I'm going to be operating this for essentially the lifetime of the plant, and I need to know if that's going to pay off today. When people start to look at the ReEDS model, there are a few indices you need to know. So I put these as G IVRHT and K underscore IVRT. Those are what I'm going to refer to as the generation and capacity variables. You should just burn these indices into your brain because everyone uses them all the time. You're going to need to know them. There's a few other indices, but these are comprised probably, or are seen in probably 90% of the equations, if I had to guess off the top of my head. So I is a technology index. So if I go through this, we have technology, vintage, region, time slice, and time. So in this case, technology is just those gas CCs, those UPVs, all these different types of plants that you have. And then you have V being vintage. I'm going to talk about that very briefly. R being region. And in this case, so it's good to burn into your brain. R can be a region. It's any region. It can be the balancing area or the capacity supply region. So we go back to this guy. R contains both P37s, P36, as well as these sub-regions of 199, all those sorts of things. That's usually what will trip some people up. And so we go through, and it's just good to know that capacity can be at the BA or resource supply level, whereas generation is always at the BA. So we aggregate up the capacity from those resource supply regions to be at the BA level. You have H being time slices, 1 through in the 2020 version, it's going to be 1 through 17. In the 2021 version, if you're interested in using the hourly representation, that can be H1 to H8760 if you really wanted to. And then T is time. So I can think of, I have generation of a specific technology, of a specific vintage, in a specific region, at a specific time slice, in a specific year. All of those things are just going to enumerate to being, this is my representation of generation very specifically, but also very broadly too. So what we tried to do when we rewrote ReEDS was make it so I can make a very condensed representation of the model by combining these indices into single for each variable. Now, associated with that, and I'll explain why we do this on the next set, is we have these conditional sets. I call them conditional sets. We can use these to, for sparse matrix construction. Basically, I don't want to consider something that I don't care about. So if I have a generation technology that is, banned, I don't even want to think about this technology. I want to be able to very quickly say, don't even see this variable. Don't even think about this variable. Don't even consider this variable in anything that you're doing. So let's say I made up a technology and I called it Max Brown. And in this case, I don't want Max Brown to be used in any of my constraints, any of my variables, but it's just sitting there because we have a lot of things that have kind of accumulated over the years and we may not want to include everything in the model. Or for example, maybe I don't want, for some reason, I don't want to include wind in my model, just to compare the differences of how much costs are saved with and without including wind in my model. We can do that very quickly by just specifying these different conditional sets. Another good example is, maybe I just want to model Texas or North Dakota, and I only want those regions to be represented. So those BAs are included in this RP set. Again, just a means by which we can very quickly shrink or grow the model and keep this general representation, this generalized representation of all these different variables, all these different indices. So these different conditional sets are used very frequently throughout the model. You can't use ReEDS and modify ReEDS without knowing a lot of these sets, if not all of them. So RFees, for example, these are the feasible balancing regions. Then you have RFees cap being these feasible capacity regions. You have T model T, which is the current year to be modeled. And then you have your val cap, val gen, and val investment. Val cap defines a valid combination of I, V, RT that can be used as capacity in the model. Val gen defines IV-RT combinations that can be used for generation. And val inv defines valid IV-RT that can be invested in that T. So all of these come together just to create the boundaries around which ReEDS can operate. So an example here, if you're very unfamiliar with GAMS, I would read this as my equation for load constraints over the dimensions of RHT if, so this dollar constraint you can translate is just a quick if R fees R, so if R is in R fees and T is in T model T. So this is saying I only want to represent the load constraint for those regions that I'm modeling and for those years that I'm modeling. In the same way, so this is only going to populate that constraint if those conditions are true. And in the same way, in several equations, I'm summing over, I need to aggregate my capacity up, whether it's for capacity credit, whether it's for, some silly constraint that Max made up because he feels like it. I need to aggregate up my capacity, but I only want to include capacity that is in this val cap set. So I only want to include those IV-RT combinations that are in val cap for the capacity aggregation steps. Why do we do this? Well, if we think about the dimensions of the problem, my technologies, we easily have 250 technologies in ReEDS. We usually have 30 vintages, if not way more. We can have 134 plus those 356 supply regions, and then we have 15 to 40 years being modeled. If I don't subset these variables, if I don't include those conditions on them, I'm going to have 55 million different combinations of these. With the 17 time slices, I'm over a billion. So I need a way to say, hey, ReEDS, I know I wrote all these very general variable and constraint definitions, and I need a way to say, hey, ReEDS, only consider these combinations of these at this time. And it very significantly reduces the model size. Before, if you find an error and something's going wild, it's typically in these conditional sets. Capacity binning, I don't have much time, so I'm not going to go through this very quick. It's just, if I were to explain this in a minute, we have two different types of capacity binning, and those are defined with that V index. Remember, all of these technologies, all of these representative units that can generate or provide capacity are indexed by V. And there's two different types of V. There's really, I'm doing the V symbol, but there's really init1 through initx, whatever the user defines as the initial amounts of capacity. Now, those are the capacity that exists as of 2010. So we start with this initial amount of capacity, and it can die off over time. And then you have the new capacity in the new bins. And that just says you can build this different type of technology in this certain year of this certain vintage. I'll explain that in 1 second. But init technologies, so the first historical, existing units are binned by their heat rates. And then new technologies are binned by, we can make a different plant available in each year. And that's all user specified. So for historical binning algorithms, see write-hintage.py. For the future binning specifications, see user input. So I got 10 minutes left. So the logic behind this is when I was first building out all of these constraints, what I really wanted was the ability to represent every single unit and have a new shiny plant available to the model in every year. Now, when I did that, the model just became unsolvable for the most part by 2050, because you kind of have this snowballing effect of both the old vintages and the new vintages. So what we tried to do, and what we were pretty successful at accomplishing, is like, let's just, if these plants are pretty similar, let's just aggregate those together and call them a single vintage, or a binned vintage. Then you have historically binned vintages and future binned vintages, and the historically binned vintages are based on the observed heat rates that are coming from the raw unit data, and the new vintages, so those that are able to be built, are defined just by model years. And so, for example, if I'm thinking about just a gas CC plant, and I go to, I can open this up for you. Open inputs, user input / ivt.csv. Oh, it's still. Where is it? Oh, yeah. So in this ivt.csv file, what we'll say is, for example, different battery technologies. There's only one representative battery unit that you can invest in from 2010 to 2018. And then in 2019, this new shiny battery 2 unit comes available. After that, so I can only invest in this vintage of battery 2s from 2019 to 2020. And then there's in 2021 to 2022, I get this new battery available to me, but I can no longer invest in my old battery unit. So in every single year, I just am able to, well, not in this case, every other year, a new battery vintage becomes available to me. And this is different. I could make a new vintage available every single year, but that just becomes cumbersome for the model. Main power system constraints, cover these very quickly, is we just have these capacity equations in motion. We have the ability to reflect how capacity moves through time. We have the supply-demand balance. We have transmission, operating reserves, and then the planning reserve margin. So we'll go on to just some of the actual code. I'm going to try to pick out a few useful things for you guys to think about. One thing to be aware of that's just really helpful is we have this I index. So if I think about B inputs in a very general sense is organized as sets, parameters, data, and then we go on to C supply model, which is other constraints, and then we go to C supply objective, which it contains our objective function. Then we have D solve prep. In that first initial few steps of B inputs, what we're looking at are just the dimensions of the problem. So we can think of, here, I'll go here, 2010. So we have the set T. You're going to see it everywhere. That defines what years are being modeled. And we can say 2010 to, in this case, we define as end year, being that's a user specified end year for the model to run. We go through these vintages. So I remember we have this technology class, init 1 to init 5, 10, whatever the user specifies as the number of vintages that want to be available. So I can say, oh, I want 9 bins, 10 bins for heat rates for existing units, however many I want, down to the unit level representation. Or maybe I just want 2 bins to represent the 2 different initial heat rate categories. And then we have our new classes. One important thing is that GAMS allows for subsetting. So in this case, I included my V technology. So my technology class or my technology vintage here, I'm calling that V, but then I can use these init V and new V to define subsets around that V. It's a little easier to see with things like this VREI. So one thing that we do is we don't always want to explicitly call out, all of the VRE text, VRE being variable renewable energy. So I allow GAMS then, or I tell GAMS, hey, all of these technologies belong to this subset. Meaning, oh, well, I can include my wind, my PV, my CSP, my geothermal, my offshore wind, all into this VRE class. And then later, if I just want to sum over those technologies, so for example, in my curtailment constraint, I typically sum over my VRE technologies there, I can use this condition as a subset. So I can say, oh, sum over I, $, or if, VRE of I. So we go through this. There's a lot of different things that occur here. But mainly, B inputs will load in your parameters. C supply model will contain your constraints. So we define the positive variables up front. We typically, limit ourselves to the positive domain for most variables except for emissions. And we're going to define all these parameters. I'm not going to go through these. I would recommend going through at least looking for the bigger ones. So the bigger ones being generation, capacity, operating reserves, gas used, those sorts of things. We define only one single positive or free variable, meaning it can go into the negative or positive domains as emissions, because if you have direct air capture represented, you can essentially have negative emissions for specific balancing areas. We define our equations. So up front, we have variables, we have equations, and we'll go into actually defining those equations. I like to start with this equation load con, just to say we already indicated, okay, so here's my equation load con. I had to define it up top if R fees R and T model T. So what I'm saying here is just very simply, the endogenous load to the model must equal the exogenous load, the static exogenous load, plus a few other parameters. Our EV load con here, we're summing over different dimensions, all these sorts of different things. For the most part, we divide this up to being load constraints, capacity constraints. We go into fuel constraints, policy constraints, all those sorts of things. It would be hours for me to go through every single constraint here. If you have questions about specific ones, I'm happy to be responsive there. And I mentioned before, so I'm going now from C supply model to C supply objective. I mentioned before we divide, so this is going to be specific to the 2021 version, which will be released shortly, but the logic is still the same, that we divide the objective function into two different components. We have the investment portion of the objective function, and then we have the operations component portion of the objective function. We take operations as just equal to whatever that PVF, the present value factor for O&M, times the operations. The investment portion is the present value factor for capital times things like, oh, here's my cost of capital financial multiplier times the cost of capacity times investment, meaning I multiply by some factor the cost of capacity times the investment to get my investment costs. The last thing I'll cover here, there's desolve prep, going very quickly through this. We define the dimensions of the retired tech sets. We go through, we define what kind of T load sets you want, our reporting scripts, all those sorts of things to get us ready for desolve 1 year. Now, desolve 1 year, the first thing you should know is unless, so we put in these checks here. So this is just an if then, if we call this T check, current year is greater than the switch for the skip auger year, what we're going to do is we're going to say, okay, T load T. So this is another one of those subsets. We're going to load in the data from Augur. So Augur will output, this Gdx file, reads Augur / Augur data / reads Augur _ current year. We're going to load in and replace these parameters that are written by Augur. And then we're going to do the operation. So for example, our old, the amount of curtailment from existing capacity as of that year is we're going to specify that. That's used in the model, in C supply model. We define that, but we only populate it when we get to this step. So for this current year, for this T load T, load in this old load, load in curt min-gen, load in curt marge, do all of these different operations using that Augur data that we specified. And then we go down, keep going. We say T model T, remember this is the dimension, this defines the dimensions around which we are solving the model. So we're saying, okay, solve, in the beginning, solve no, don't populate anything, but T model T of this current year that's passed as a global argument to GAMS desolve 1 year, say yes, AKA we're going to solve the year that we want to solve. We're going to solve the year that we're specifying to solve through this current year argument. And then solve ReEDS, minimizing Z using this linear, using LP. And that's just a very GAMS specific thing. Z is the name of our objective function value. We called the model itself containing all those equations, all the constraints, all the variables, all the data. We called that ReEDS model, minimizing Z. So solve that model, minimizing the objective function using linear programming. Record the objective function values. And then at the end, what we do is we say D2 varfix. What D2 varfix does is if I solved you, so this is specific to the myopic solve or the sequential solve, D2 varfix will take the values that resulted from that solve and fix those. So for example, let's say in 2022, I invested in 100 megawatts of a gas CC plant. If I didn't fix that variable and I start solving 2024, that variable becomes free. I'm allowed to invest in whatever I want in previous years, allowing me to correct potentially poor investment decisions. So I fixed that investment, and then when I solve 2024, my 22 values are seen, but I can't do anything with those. I'm stuck with my decisions. So at the end of each solve in the myopic situation, we say, fix your capacity, fix your investments, fix your load, fix your generation, so that whatever you did in the past is fixed. And then finally, we have D3 Augur data dump. This prepares the data from a solve to be used in Augur. Finally, almost finally. So at the end of this, so we do that solve sequence. We say, we're doing the 2010 solve, 2012 solve, going all the way through to 2050. And then at the end of that, we have a couple different reporting scripts. Stuart's going to cover a couple of those, but the one to be aware of here is just eReport. And so eReport, at the very end of a solve, you can then take all the information that exists as of 2050 and start, reporting what was the generation for every year, what was the capacity that existed in every year, what were the operating reserve provisions, what was the capacity credit available from PV plants, all these sorts of things that you may be interested in. What was the energy price, for example? We calculate all of that in eReport. So there's things, a lot of parameters written out here, but just to be aware, at the end of the 2050 solve, so we desolve 1 year out to 2050, we run eReport, and we gather all of this information, and we execute, we dump that information into an unload. So we say, compute all of those parameters for us, and let's dump those to what we call rep_fname, or this fname is just your case name. So if I ran my, demo1_reference case, it's going to run all the way through 2050. It's going to run eReport and then dump this GDX file called rep_demo1_reference. And it'll take everything we used in that report. And then finally, we have eReport dump. And so we needed to do this because the calls to GDX dump here are execution and not compilation time calls, meaning if I were to run this at the end of eReport, it would do those first because it's going to see those and do them automatically. So I need to call eReport first, dump that GDX file, and all these are doing are writing the parameters that are used, the parameters that are calculated and sent to the GDX file. It's writing those to CSV files that are included in the outputs folder. So a lot of things I just covered. Tried to get it all through. ReEDS is rather complicated until it's a very steep learning curve, but once you actually start using it, you'll get a good feeling for it, I'm pretty sure. So you'll be able to start doing these modifications, adding in new constraints, doing new reporting, adding new data, all those sorts of things. I tried to give just this broad overview of how to think about the model, how to think about running the model, and how to get to the point where you're running outputs, creating new reports, those sorts of things. So I think I'm out of time, but I can keep going if anybody wants me to.
Yeah, I'm sure you keep going here. There's so much to cover here. This is great, Max. And I think just for everybody who's gone through this, so Max has kind of given some overview pieces. You'll see a lot more kind of practical pieces through some of the next hour of just like more of how this works. So we'll go ahead and take a 5-minute break here, come back at the top of the hour. That'll be 11 o'clock Mountain Time. And then Stuart will take us to the next section, and then I'll end with debugging at the last portion. So yeah, we'll be back in 5 minutes. Welcome back. So Stuart is like next to kind of walk through some more of the file pieces, and anyway, he'll show us some more after Stuart's done, which he'll take roughly 30 minutes-ish. Then we'll shift over to me, and I'll talk through some debugging pieces for the last half hour.
Hey, great. Well, I'll just jump right in. So what I'm going to cover is largely on the kind of input and setup side. I mean, I know there's at least some people that download the repository really just look at the input data and take that and use it for whatever models or tools they're working with. And so I do want to get into a little bit more of what all's in there, what it looks like, how the ReEDS code uses it. And a good place to start, it really is going back to this cases file. And so a lot of the switches in here actually involve, choosing different input data sets. For example, a lot of the ones near the top, so I'll take UPV scenario, for instance. And so the default value is this, at least in the open access version that's out right now, is the ATB 2020 moderate pathway. And this is the default switch setting that you can, add a column for a new scenario and then change it as you want. And then the way that this particular switch setting is used is that it's actually part of a file path for the input data that's, the utility, PV, cost, and performance characteristics. And so there are a lot of these, particularly on the technology cost side and fuel prices and load scenarios, where the purpose of the switch setting is actually to specify which input file to use. And those input files start out in, the open access ReEDS inputs folder. And so, for example, not that one. So that particular switch would direct you to which file to choose for UPV in this plant characteristics folder. And so we've been doing this for a while. There are quite a few choices to work with, and you could even create your own. You could do that just by saving as a different file name and then, putting the name of that file in this row for the switches. And what that looks like is just it's just a table basically of capital costs, FOM, VOM, and relative changes in capacity factors over time for utility PV. And so that's just kind of one example of how the cases file interacts with the input data. And another thing that I pointed out in the chat is that in many cases, though not all, if you were to, copy and paste this and then, edit these numbers however you want, for that to actually get used, you might need to go into this files for batch CSV and then just add a entry for it. The reason why sometimes that's necessary and sometimes that's not is because the way that the inputs are processed are that first, we run a lot of these Python scripts using awrite data. And if it's a raw input for these, you don't need to include it in files for batch, because what ReEDS uses is actually outputs from this, and then the outputs go where they need to go. And I think that UPV file is actually an example of that, because you can see there's no UPV data files in this list. However, some other files, if they're processed directly by the binputs script, those need to be included in the files for batch. And that's why you'll see there's a long list of, a lot of these files are input files in addition to, obviously the code files themselves. So that's just kind of one example of how some things fit together. But I do want to also point out that, there's a lot of cases, there's a lot of switches. It can be kind of overwhelming to open this up. There's a lot of things to play with. And we do have them described in the README. So if you go into the GitHub page, there is documentation of the model switches. You're welcome to be critical of this and point out things that we're missing, because I feel like we probably don't do the best at necessarily updating this to list all of the individual switch options and what they all mean and have that all be clear. So, just generally, I think we would all appreciate any feedback and kind of criticism on what's missing there. And, we could even open up a discussion around that on the discussions page. But that is definitely your first place to look to understand what are the switch settings associated with all of these switches and how are they used. Let's see. And then another thing that I mentioned in the chat is the idea that it's best practice to kind of keep this raw cases.csv file as is. And so the repo always needs a cases.csv without a suffix, because that is actually what the scripts use to know what are all these default values. And so you could run from this, but it's a good practice to always sort of save this as something else with a suffix and call that. That way, if you could actually slim this down only to the switches that you're changing. And so I just ran an example, and well, this is bad practice because I just changed the default to 2012 as opposed to putting it here. But oops. But really, if I wanted, I could have just ran this whole. I could have just saved this as this, and it would still work because it knows all of the other switch settings from that base cases.csv file. So that's just something to keep in mind, so you don't start to run into errors around looking for input files or looking for switch settings and not knowing how to specify things in the model. Let's see it. So what I want to do, and I mean, last year I went through a pretty comprehensive look at what all of the inputs are, and I don't want to sort of repeat that because that is something that is available on the YouTube page. But I do want to continue. I do want to reiterate some of the key things and some of the changes that show up, at least in this directory. And I want to keep it to what's out there right now, so anyone can sort of follow along. So a few key things to keep in mind. So this is actually changed to a CSV in the 2021 version, but this hierarchy file is fairly useful. It actually, you have to get familiar with the indices, but what this actually is a mapping between all of the different regional aggregations in the model. And so there's some smaller, some slimmed down versions, like this maps between balancing areas and resource regions, and this maps, actually this is a little different, between balancing areas and census divisions. But if you're trying to really dig into what balancing areas, resource regions, whatever, are in these different levels of regional aggregation, RTOs, census regions, states, interconnects, this is a handy file to use to classify, to categorize those things. So that's just one I wanted to point out that's in there. Another one is this text subset table. So you might want to, like Max pointed out, all the different things with like conditionals. You might want to create a new constraint that you only apply to certain technologies. And so to do that, you can create a new subset, and you have to do this in the GAMS code as well. But this is a handy file to where you could add a column for a grouping of technologies, and just add them, just write yes wherever it should apply, and then you can create that subset in the inputs, which is around here somewhere. So here's examples of these subsets, and then there's code already built in. So you'd have to add the column name in this I_subtext, add the subset name over here, and then once you do that, all you have to do is populate this table however you want it, and then there's code to read in and process that subset, and you can use it anywhere else in the code. So that's another handy kind of root input file to be aware of. And then there's other things in this root directory, like this defines how requirements for operating reserves, Another potentially useful file is this deflator if you want to know how ReEDS is converting between dollar years. This is, the CPI index that we're using for that. And that also gets used in certain places in the input processing, so that you can actually, there's a couple scripts where you can say like this input file is in $2019 and that input file is in $2014, and then it can use this deflator to get everything converted to the right dollar year. So just to kind of go down, I mean, a lot of this stuff is obvious. So this is defining Canadian imports. I think the capacity data is one of the more messy directories, but also has a lot of useful information. And so the key file here is really this generator database file. And so if you're interested, so like Kara Marcy presented last week on how they are adapting EPA's needs database for ReEDS, and that really has to do with kind of coming out with an alternate version of this database file, in addition to this prescriptive builds and prescriptive retirements information. And I'm not sure if this one's actually still used. Some of these formats are kind of legacy. But this folder has a lot of the unit level information that ReEDS aggregates using whatever you define for like how many vintage or Max's hintages, historical vintages that you want. So there's a lot of information in here. Not a lot of it gets used. This is based on NEMS input data, and so certainly not all of it is easy to interpret what all these column names are, but if it's something that's important that you can't figure out and just use based on the already processed input parameters, this is kind of where it all starts. And so you can see other things in here like that might be important. Like if you wanted to change the first year that something could get built, you would do that in this first year's file. If you wanted to change the physical lifetime of a technology, you would do that in this max age file. So there's a good number of useful things to manipulate in here that you might want to play around with, depending on scenarios. Carbon constraints has forced retirement of a coal plant. So I think I got that before the little window went away. So the way to do forced retirements for coal plants, I think there's a couple ways. So there is I should not have cleared cases. There's a retirement scenario. I know there's a switch that we've used in the past to do coal lifetimes. Yeah. So we actually have a switch specifically built to play around with coal lifetimes. Camp switch coal retire. And I don't know, Wesley, stop me if you think this is like taking too much time. But I believe that gets used to, you can create an additional option with this switch and associate with it a kind of change in lifetime. I don't know why it's not. There we go. So here's a couple examples. So we've got a couple settings here. One where it looks like it subtracts 10 years, one where it adds 10 years. So you could play around with that one, is what I would suggest. Or you could go into the database file and just edit them, if you wanted to do something with specific units. I think another one worth pointing out, this carbon constraints folder. So if you want to, You create CO2 tax scenarios, cap scenarios. Okay, good, great, Thunder. This is where you would manipulate those. Capacity factor data, that's what's not too exciting. Renewable resource data, construction schedules, construction times. These affect the financials, CASPER policies. Degradation is actually a newer one relative to last year anyway. So this is defining, basically capacity of degradation of PV and wind over time. And so if you wanted to say like the capacity of something else changed over time, so this is a rate, year on year, you could go ahead and, add a number for some other technology if you wanted to. Demand, this has the demand side module information that we haven't used much of late, so I'm not going to get into that. Depreciation schedules, DGen is the rooftop PV data, financials. So, say you want to play around with, the book life or the debt equity ratio for different technologies, this is where you would do that. And you can actually create new scenarios around that as well. And so the core file is this ATB 2020, and you can see where you can change depreciation schedules, evaluation period, that's the book life, construction schedules, and then we have these adjustments in financing factors that I'm not going to get into how these are made because I also don't know it really quickly off the top of my head, but they have to do with, like if you have a tax credit policy or something like that, that changes how you would finance debt equity. This represents a deviation from the kind of nominal assumptions, which are in this system financials folder. So here's where you have, nominal interest rate, nominal rate of return equity, debt fraction, tax rates. You can see how you can make these change over time. Obviously, based on you can see the change in tax policies from the previous administration are represented. So yeah, you can play with a few different things. The construction time, so winding heads. So the constructions, let's see, it's actually in the schedules. So if you want to know sort of what the kind of labels for the construction means, you would go into this construction schedules. And this is just saying so like 3B means it's a 3-year construction. You spend 50% in the first year, 40%, 10%. And so that helps us account for interest rate during construction. So you could make a new one of these if you wanted, and then set it to that as well. And I didn't catch the other question that came through fast enough. Let me open up the chat. What file defines technologies that fulfill RPS? Yeah, we'll get there. Definitely want to, yeah, obviously these policy discussions are really important right now, so, and making the news a lot. So I definitely want to point those out. So I think it was about DGen, yeah, financials. These are the, Max mentioned the alternate fuel price scenarios. This contains the files that define those. Geothermal has its own special folder around alternate supply curves and FOM costs. That's not exciting. Okay, Wesley gave me a 10-minute time check. Incentives. So this one, if you're interested in doing analysis on, what if PTC or ITC policy changes occur. This is, can't remember which one of these is default, but so these kind of second parts of the file name are part of switch settings, and so you can specify which of these files to use or create a new one. And so this is defining PTC and ITC values, durations. how that affects tax equity for relevant technologies. And so you'll even see here that there's something in for like CCS technologies, and this is the I would say incomplete but non-zero way that we represent the 45Q policy. So I could get into that more detail, but I don't want to take the time for it right now. Inflation, load data, if you wanted to change load scenarios, this has all the information, particularly like this is all the electrification futures scenario data defining future electrification load and as well as flexibility of that load. So this is, kind of, you can download the raw data from our electrification futures page, but this gives you a sense of what ReEDS sees. And now I can answer Claire's question. So the ReEDS has a couple different constraints, some of which interact, which makes things maybe a little bit messier to use. But the key one that we use to define things like national RPS policies. Well, can't find it in here. I don't know why this is not being easy to find. Gen mandate, this is it, yeah. So if you flip this switch on, put a 1 here, it's going to activate a constraint that essentially says a certain percentage of generation in each year has to come from a specific set of technologies. And the parameters of that are defined in this folder, where this netgen frac defines the percent required. So this is saying like, 80% of generation in 2050, and you've got to have a number for every model year at least, which is why this is every year. The 2021 version, this is a little bit different. We actually have multiple columns for different scenarios. And then there's a second switch that allows you to just pick which column to use. So that'll be a little bit different, but same idea, just a little bit easier to run batches of different alternatives. And then if you want to define which technologies qualify, you go into this folder where you can actually put anything between 0 and 1 if you want to give something partial credit. And so right now the default is Canadian imports are just assumed to be primarily hydro, so that qualifies. And then you have all your renewable technologies. But like if you wanted to make CCS eligible, you could enter a 1 here. If you want to make CCS and nuclear, if that's how you want to represent a clean energy standard. So this is where you would manipulate which technologies qualify for a national RPS policy. And then if you're referring to state RPS policies, those are all defined in these files, and I'm not going to dig in too much detail because of time, but here's where you would sort of define what those policies look like and what qualifies, what are alternative compliance payments, all that good stuff. I want to point out, so plant characteristics, this has a lot of the ATB data, the annual technology baseline. So this has a lot of the cost trajectories and performance trajectories. And so if you want to create new scenarios around that, or just see what that looks like, this is a good place to look. Supply curve data, I think is fairly straightforward. So, in some cases there's alternative supply curves, but this is, for most renewables, we're talking about the interconnection supply curves. So the incremental cost to connect to the backbone transmission system as a function of the capacity, and so there's different bins, meaning like the more you build, the further away you have to connect. But some of the data is actually, kind of a raw, like the total capital costs. So that's the case for hydro and pumped hydro, and we're going to have new pumped hydro data and we in CSV form. But just as an example of kind of what that looks like, here's the resource, the classes, and this is the total capital cost, not just the interconnection. Let's see, transmission, upgrades. So Wang and I were discussing this upgrade link file that helps define upgrade pathways. If you want to add a new one, you could do that. Value streams, what else is new that I want to point out? So I'll point out the water climate stuff real quick, because I think this is new in 2020 and it'll have some more information. But if you flip the switches that expand the technology set to represent cooling technologies and water sources, this is a file that has the information that how to do that basically. And so it has changes in cost and performance associated with different cooling technologies, dry cooling more expensive, lower efficiency, and it's also got water availability data to constrain water withdrawals or consumption depending on the technology and water source. So that information is there, and then the 2021 version is going to have some of the actual climate projection data to activate that representation as well. And I think it's actually going to be in a separate folder, just named climate. Variability. So this folder, if you want to dig into the hourly data that's used in Augur, that's in here, but that'll probably be covered in more detail on Thursday. So I won't dig into that really. And then I think that kind of covers like the quick overview of inputs. Max already pointed out this IVT file, and this is where you can define different sets of model years to run. But the last thing I want to do just really briefly is almost kind of a sneak preview of tomorrow's session on outputs. And just pointing out that, when you run a model, Max pointed out this inputs.gdx, which is a great place to look and see what the model is actually seeing and if that matches up with what you think you did on your input side. But then obviously when you look at the outputs, that's very helpful too. And so I just ran a really 2-year simulation to have something to play with. But one of the places you would look is go in the run folder, go to the outlooks, and really the first thing you do when opening run is just open up one of these HTML files. And so there's 2 that get automatically produced, and one's just bigger than the other. And then you can start to look at what is the generation mix, capacity mix. This one looks silly because I only ran 2010 and 2012, but it'll give you prices. I don't know why that output. I think that errored out because I only ran so few years. It doesn't know what to do when you only run a couple years. But then there's another one that's got a lot more detailed information. So like operating reserve information. So this is kind of the first place to look. And then where this comes from is actually the bokeh pivot tool that Matt Mowers will describe tomorrow in a lot more detail. But you can start to play around with that just by going into the bokeh pivot folder, and if you just hit launch.bat, and hopefully that works because I haven't used this machine in a while, all you've got to do is open that up and then tell it where a run folder exists. So you can actually do a folder with many runs, or you can do a specific run folder, and it'll work either way. But you just put that file path in here, and then you could even rebuild those same reports very quickly. So I'm not going to get into the result stuff. That'll happen tomorrow. But one of the nice things about this is that if you put in a path with many run folders and then build the same report just by going, build report, pick which one, So reduced, extended, whatever. You can make your own, but I don't have time for that right now. You can then add differences, and this isn't going to work because I only have one run in this folder. But what that'll do is it'll basically make the same report, but it'll have side by side for each scenario. And for each output, it'll say, what are the differences between all the other scenarios and then whatever you specify as your base case. And so that's super useful when you're running batches. Obviously you can really see the incremental impact of all of your switch settings. And so, highly recommend whenever you run a batch, just going immediately into here and running one of these, what we call a compare report, because then you've got a one-stop shop to see what's going on across all of those runs. So I think that gets through what I was intending to cover. Wesley, do I have any more time, or should we just move forward to debugging?
I think I'm going to go ahead and start the debugging just so we get there. If I haven't timed this, I don't know how long it's going to take, so we can always come back here if we end up with a little time at the end.
Yeah, and if there are other questions on this stuff, I'll just answer them in the chat.
Yep, so feel free to send in more questions here. So share my screen. So what I want to do is just kind of walk through some things you might see as errors as you go through things. So ReEDS, it's really easy to break ReEDS. If you've tried, you've probably already learned that. But it's also usually not that hard to fix it. So hopefully we'll give you a few ideas here. So I'm in my directory already where I've got everything there, and you saw Max just doing the Python run batch.py to kick off a scenario. So that's what we're going to do. But I'm going to just kind of walk through where you'd see errors. So the first place you might see an error is in run batch. If you see an error in run batch, it's probably because you're missing a package. So we're just going to come in here and we're going to create an error in here. So I've got the run batch file open because usually you never have to touch the run batch file. I'm just going to comment out importing a package. So it'll throw an error. So I'm going to start a case and we're going to just call it A1 today. And everything I'm going to do is I'm going to run with the test suffix file. So that's already in your repository. You already have a cases test that's in here that just runs the ERCOT system. So it goes really fast, and I'm running it because it goes fast. And I guess one other caveat here is I am running our beta version of the 2021 model because we made the test model even faster, and I want that speed as we go through to debug in real time here. So it should look almost the same, and the experience will be the same, but just if you see something different, that's why, is because I'm using the newer version that has a faster test system. So I'm going to tell it I want to use that test file for the cases, and then it says, oh, you've got a problem. It's trying to find this threading thing. You'll see something similar of like, oh, shoot, I'm missing a package. Let's get that fixed. So we'll go ahead and change that back so we can see what's going on. So that's, if that's the first place, if you get an error before anything even happens, that's, you're in run batch. You haven't even got to where it's kicking anything off. So the second place you'd see the error, the next place you'd see the error is if you remember from doing a run. Let me go back to this. I've got a run that I ran ahead of time here that I called demo. Max was saying that, the way run batch runs is it creates this folder and then it makes this shell file or batch file. I'll just stick it in here. That, just changes your directory. It runs the create model and then it starts running all these commands. So we'll come back to this a few times. But that create model .gams has the 4 pieces in it that, let's pull it up. Create model has it just says, well, do the right data, then do B inputs, then do C supply model and C objective, then do sol prep. So the next place you often run into issues is in A write data, which this is the one that calls all of the Python scripts. And if you've seen in the repository, the public one, we've scrapped the R scripts and everything's Python's made installation a lot easier because you don't have to have R dependencies. So there's just a whole bunch of calls, Python calls. So it's running Python fuel cost prep.py, Python writecap app.py. These are all in this this input processing folder. Here's where all those Python scripts live that it's running. And what you might have here is that there's something wrong, something happens in one of these files, and then that creates an error downstream. So all of these files, they read inputs and then they write out something at the end. They're usually writing out a CSV file at the end that ReEDS is going to need to do its to make the model work. And so if it fails somewhere along the way, it won't write those CSV files. So if you get an error that says a CSV file is missing, that's likely that you have an error in one of these places. Let's create one because it's something that you might see, and it's something you might want to do here anyway. So Stuart talked about making a new cost trajectory. So let's say we want to run a new case with PV, and we want to make PV cheaper. So let's say we're gonna make a new case. So we're gonna build it off of this file. And again, I'm using the 2021 beta version, which is why there's 21 values in here. So let's rename this, and we'll call this. It's going to be. We'll make the costs half, so we'll call it moderate half. So I've made a new file, and all I want to do in here is we're going to change the capital costs. We'll start in 2020. We're going to make them all 50% of what they are before. So we'll take these values, and we'll say let's make them half of what they are. So okay, we just made them all half. So now we're getting down to $300 a kilowatt by 2050. We'll save this guy, and then we're going to go. We're going to go to our cases test file, and we're going to add. And well, I want to open up my cases so I know what the thing is I want to change. So cases, and I want to find my UPV switch. This is what I want to change. I'm going to change this. So I now want this switch. So I'm going to bring it over to my cases test. And let me simplify my file a little bit so it'll look more like what I'm going to delete this one. I'm going to delete this one. So this will look more like what it looks like in the current repository. So like Stuart was saying, I've only adjusted the switches that I want to change. And now I've added one more thing where I've said, well, I'm going to change the UPV scenario, and I want to change it to our new file, whatever our new file was. So we want to change our UPV to this moderate half. So we're going to make it say, instead of use that file as the input, we want to use our new one we just made. So, okay, so we're going to do this. And now we come over and say, hey, we're ready to run now. So let's do Python run batch. And now we're going to do our second case, A2 here. We're still running this test suffix. And it's going to start going. So you can see now it didn't error right away. We don't have the run batch error. It's starting with the investment calculations. It's starting to go. It kicks out a new screen. So this is where it's running the batch file. And you can see all these calls to Python that it's making. This is the write data portions. And then it just stopped now. It's well, that's way too fast. Can't be done already. ReEDS takes longer than that to run. So let's go look at our run and say, hey, what's wrong here? We thought we did everything right. I don't know what happened. So we come in, and one of the output files here that's really useful to look at is this GAMS log file. So we open this text file up, and this has something close to what the console had. So again, this is what Max was talking about. Here's all our switches that got put in, and then here's all these calls to Python. And down here at the very end, you could see that when it was doing the Python plant cost prep, and hey, that's the key. We were changing the plant costs, and it's the plant cost prep that's just throwing an error. It's saying that there's an error in here, that on this line there's an index out of bounds, and we could, if we were like, hey, I don't know what's going on, we could go ahead and just open up that file. So So let's do that input processing, and we're in plant cost prep. And it told us the lines. We were on line 74. Is that there's this deflate function that's trying to find a dollar year and matching it with a deflator value. And then it's, you could see what's happening. That's taking this deflate value and it's saying, hey, multiply your capital costs, your FOM and your VOM by the deflate. And we say, oh yeah, we didn't tell the model what dollar year this data set is. We made a new file and we just gave them this data and said, here, go. But it's failed because we didn't give it a dollar year. And you could see this here too on this, line 99. You come down, that's where it's calling the deflate function. So it's saying, hey, apply the deflate function to our UPV data. So we'd have to actually go back in and say, okay, well, let's fix that. So we'd go into our inputs and you'll see in our plant cost prep, there's a dollar year file that has the dollar year for every one of these pieces that we're looking at. So now if we said, oh yeah, okay, we added this new case, we'd have to stick it in here. We didn't change the dollar year when we changed this data. We just made it all half. So we'd be the same dollar year, and then we're done. So this will work now. We won't go through and demonstrate that it'll work, but that's the piece that was missing. As we hadn't done this, you can see that didn't create the file that we needed. It didn't create the outputs. It failed in Python in this awrite data step. And then we're able to see that in the GAMS log. So this GAM log, a great place to see that, what happened. So the other place that you could look to, let me go back to this runs folder, is in the LST files. So these LST files are they're GAMS listing files that have outputs from GAMS. So we could come in here and we could also see the same thing, that it's, if you search for these 4 asterisks, here they're at the beginning, it's easy to see where they're at. 4 asterisks means there's an error. So you could always search these listing files for 4 asterisks. It's saying we have a 343 error on this line, and it just said abort triggered by this statement. So you could also see, okay, it's a plant cost prep file, and this doesn't have as much information as the other one because it doesn't give us the Python error. But at least, oh, it's in plant cost prep, and we could go there and look. And if this was a more complicated error, it wasn't just like, oh, we could figure it out. You could always come in to the plant cost prep file, and we've got, you could come in and just set all of the parameters. You could see these commented portions where we've already done this kind of thing where we're set the inputs, and then you could just run through the code line by line to debug if you needed to. So that's the second piece of, if you get an error in this upstream before you even get to the model. The other kind of place that you'll get an error is, especially when you're changing things in the model. And often when I'm writing code, I don't write it correctly the first time. I'll get some sort of error. So let's do something like that where you get an error now in the GAMS code. So we moved from the Python code, now we're in GAMS. So we're going to be in GAMS, and you get an error in the GAMS code. So I'm just going to come down and do something like, hey, I'm just going to take out the semicolon. That's going to create an error because GAMS doesn't like that. So I'm just going to make an error in the code. And now we're going to run it and see what happens. Let me get rid of this piece. We're going to undo our, well, actually, we'll just go ahead and leave it. And then we could, so we'll come back to this guy. We're going to run our run batch, and now we're on A3. Let's be more descriptive. This is now our compile error, what we hope will be our compile error. We're still running our cases test. So now it starts going, again, does the financials first. So we wait for it to get through those, and then it'll kick out the new window. When it kicks out the new window, that means it's running the batch file. So, you could manually do that if you wanted to rerun one. So again, running through all these Python calls, and this is why I'm using the 2021 version, is because this script right here takes like 2 minutes on the older version, and I didn't want to wait 2 minutes while we're moving through things. So we sped that one up quite a bit for this year. That's the script that goes in and pulls all the hourly load and resource data across 7 years. So it's really large data sets. So it could take a while to pull all that data together. So, I mean, you don't have to sit and watch screens. Like when you're debugging, all these output files will be there. So I rarely debug in this kind of way of just like watching what happens. You could get all the files as they come out and see what's happening. And you could even, if you have a run going, you could come and monitor it as soon as it's kicked off. It has, it creates the folder already. So that's already here, and you could kind of see where it's at. So we could, it's already copied the files over. We could go into this Lst Files folder, and you could see the input is the only file, and it's 0 kilobytes right now because it's still writing to it. So we know it's in this early stage just by looking here. We didn't have to. So if we're not monitoring it, that's still fine. Okay, cool. So now you can see it's running B inputs. Oh, I wonder if I saved it. If I didn't save it, then it's not going to fail. It looks like it didn't fail, so I'm guessing I didn't save my B inputs file. Okay, well, we'll start another one. Nope, it's solving fine. So we didn't make it crash. Either that or I'm in the wrong file. So I'm just going to go and kill it. And then we'll try it again, and we'll come back to it in just a minute. So we'll call this compile error 2, and we'll let it go. And while it goes, have one to look at there. I'm going to pull up one other piece that I ran an earlier case, where I put an error in eReport. So eReport is the last thing that gets run. So let me go back to this actually. So as you're running through, it solves. So it does all the input stuff. It solves, solving the 2010 year, the 2012 year, et cetera. And then we get down to the very bottom. It's solved. We just said run through 2030 in the test case. So it's done, solves 2030, and then it runs this eReport, which has a whole bunch of reporting pieces, and then the eReport dump, which takes all the GAMS data and dumps it into CSV files, and then it has the calls to this OK pivot, and then some kind of output formatting things to help other downstream process pieces. So when the models run correctly, but there's an error in the eReport, you'll get here and you'll go to the outputs folder, and you can see that all the outputs are here, but you also see that they're all 1 kilobyte. So if I open one up, they're empty. It just says there's not anything there. So the model ran to completion, but I don't have any outputs. So this might be something you see, and then you look for these HTML files, and they'll be here. But then when you open them, they'll look like this, and you're like, oh, well, I don't know what's wrong. So this usually means you have an error in your I'm in the wrong one. Error in your in that report script, the reporting script. So if we go in here, Lst Files, we could see we have all the files that we were looking for, but then if I open up this report, Lst Files is the one for the eReport. It says, hey, you've got an error in here, and says you've got error 409. Unfortunately, it doesn't tell you what the error is right by it, so you have to go to the bottom, and then it's always close to the bottom, so it'll say, hey, there's an unrecognizable item. This one is actually not a very helpful code, other than it says look for a missing semicolon, and that's actually what I did here is I deleted the semicolon on the line before. So you can see actually the line before, every line in GAMS has to end with a semicolon. I deleted that semicolon through this error. You didn't get any outputs. So now I could just go in and say, well, I don't want to run the whole thing again because I already ran it. And I already have it. Everything's here. You know, Max talked about the goo files, so I've got my last goo file. So the data is all there. I just need it dumped out. So I could go in and fix it. So I could open up my eReport file and go down to where this error was, which was right here that I'm missing a semicolon. I could put it back in. I'll save it this time. And then I just want to run the reporting steps again. So I could go to this batch file that's got, you know, here's that file. There's two things I could do here. One is I could just navigate to this file and then just run this line in the command line, or you know, in Windows I could also just say, oh, I'm just gonna make a copy of this, and this is our second version of it, and I'm going to I don't want to run any of this stuff, so I'm just going to delete it all, and I want to run everything after it. So I only want to run these things. So I just want to have the report rerun and then rerun these Python pieces. So I'll save that, and then I'll come back and I'll just run this file, and it's just going to start by running the eReport. And it'll create the outputs and generate those bokeh plots. It's basically I've just picked up from where I was before because I have the restart file. You can see, you know, the first line it's looking for is saying going in and grab that restart file. I already have it. And then it'll spit out the outputs. So that's pretty convenient. So that's what's going in doing right now, doing all the output pieces, and then we can come back and check and see if the outputs are there. So let's go back to our other one and see if we actually got a, make that not distract us for a minute. So we made a compile error 2. Let's see if it ran. Oh, this one ran too. So I'm obviously not making an error right. I don't know what I did to not break this model. But the idea is that you'd get the same kind of thing where you'd get an LST error, and you could go in and look for it and debug it that way. So I'm obviously failing.
Wesley, it might not be compiling that line just based on the switches.
Oh, okay, that could be. I could have just not. Yep, I could have be changing a line that's not actually observed in the model. So yeah, thanks for pointing that one out. So another piece that could be a useful thing here. Oh, it looks like it's finished. Let me come back in here. So now if we go back to our outputs, you could see that, look, the outputs are, they actually have real sizes to them. So our outputs are actually populated. And you can see there's a new set of reports. And this is the way this happens because we have bokeh set up so it won't overwrite things already there in case you create a new set of reports. So it's actually renamed my old one as archive and then created these new ones. But these new ones actually have data in them. So you can actually see the results here. And again, this is just Texas, so that's why you're only getting 350 terawatt hours of load. So so that's helpful to be able to rerun things. The other piece that I want to point out in here is that we added this dump all data script, and this is a super simple file. So all this is this batch file in here. It just make you sure you're in the right directory, and then run this dump all data gams from your restart file. This dump all data file has one line. All it does is say execute unload all data.gdx. So if we run this guy, it'll just run that one gams line, and then it outputs this all data.gdx file, and this all data now has everything. It now has everything in it. So here's our all data. This is everything in the model. So it's got all the constraints, it's got all the variables, it's got all the parameters. So this is really helpful for, after the fact, you're like, hey, why did I get this thing? What's going on? Or You know, could we find that something's wrong? And now we could come in and start exploring this. So here I have the cap variable selected, and so we've got the IVRT indices, so you know, your technology, your vintage, your region, and your year, and the level means that's the value that the variable took. Here's the marginal on that variable, and then the upper lower bounds are going to be fixed based on that's the way it's set up. So now I could start exploring this and say, you know, why am I getting capacity here? You know, it's multiplied by the capital cost. I could look at that and say, oh, you know, I put the capital cost in dollars per megawatt instead of dollars per kilowatt. And that's why I'm not getting any of the PV built. It's because it's, you know, 3 orders of magnitude too high of cost. So you could start coming in and exploring things pretty easily with that. And if you have one that didn't finish all the way, so you maybe have a scenario you're going to run through 2050, but it failed in 2030, you could always come back to this dump all data file, and it will automatically put the end year in here. But if the last year you have is, you know, 2026, you could just change this to 2026 and run it, and it'll pull, as long as this matches whatever the name of your goo file is, it'll pull from that goo file and dump all the data out. So hopefully it's helpful in terms of, you know, how you start looking through and finding what's wrong and how to fix it. There's more pieces we could go through, but I think that, you know, the key pieces are the GAMS log file is useful to look at to help you be able to diagnose where errors are. The LST files are really helpful for, you know, especially for the compile errors. And yep, this one's gone away. We've updated LST with no error now. So this one lets you go through and see where, you know, where errors are in the code and gives you an error message from GAMS. And then that all data is really helpful for inspecting the data and making sure that things are in the right place. So let me stop sharing my screen, and we're basically out of time here. So I guess if you have follow-up questions, one, you're welcome to ask us. You know, send us a note, and we'll help out as best we can. You also, oh, I do want to keep sharing my screen because I want to show you this. Is that we have sorry, pulling it up. The discussion forum on our GitHub page. I'm slow, but I'm getting there. So again, this discussion tab on the GitHub page, you could come in here, and this is a place for you to ask questions of like, hey, I mean, this would be a great question for like, hey, why isn't there not a CCS upgrade option in the link? Or like, hey, I tried to add the CCS upgrade in the link, and it's not working. Like, you could stick that in this discussion page, and or if it is, you know, if you do, it is an issue with the model, you could create issues. Everybody should be able to create issues. So you can make a new issue and say, hey, I added CCS as an upgrade and it didn't work. Here's the error I got, and you stick it up there, and we could take a look and respond to it, and especially if it's an error, we get it fixed and push it out. So so encourage you to engage there. We're out of time, so I'm going to go ahead and close up here, but thank you all for engaging with us. This has been good, and we'll get this recording posted on YouTube, so you'll be able to watch it, or if you have new people that you know of that want to spin up on the model, they'll be able to use this to help them get along. And tomorrow, training on bokeh, and Thursday, training on the Augur submodule. So look forward to seeing you there. So thanks, everybody, and have a good day. We'll talk to you all later.